Today we'll be looking at the principles of reliable data transfer, a topic from computer communication and networking. I am Hirsha and I am from ICT 19 and I'll be teaching you this topic today. So what is reliable data transfer or RDT? It is basically a protocol used by senders and receiver to reliably transfer data at the transportation layer. So basically in our entire communication we have multiple layers of abstraction where each layer has its particular job to do. So there is application layer, and there is at the bottom there is a link layer, and everything in between them there is network layer, there is transport layer, and our particular concern is about reliable data transfer in transport layer, right? So here we are going to look at the perspective of both the receiver and the sender, and here the main problem is that the sender sends a message to the receiver but doesn't know its status. It might be that the receiver gets it, it might be there must be some loss. So thus there is a need for a protocol that the both receiver and the sender should follow, right? So we'll look into it. So for that we have the approach that we are taking is that we'll first start by assuming that everything happens ideally, right? So the whatever we send gets received correctly with no data loss, and then we go ahead and lift all of our assumptions, and that is the ideal way of learning. We are also going to use FSMs, finite state machines, which help us write the state of receiver and sender while we are receiving or sending or waiting for a protocol. That will be much more clear when we go ahead with it, right? And as we lift each assumptions, our model or our protocol will be much more closer to the end or real world scenarios, right? And the presentations must be viewed in presentation mode. So first of all we have RDT1. Here again we are assuming that everything is very ideal. The cases are ideal where the sender sends the message and it sends it over a reliable channel. So it is very sure that the receiver will receive it without any issue, right? So FSM, here the FSM says that the sender will wait from call from above. Above means from the application layer. Application layer sends it to the transport layer, and so it will wait from the call from above, and then it will send the packet, and then again it will wait for the next packet. The packets are transferred one by one, and in the receiver side it will wait from the call from below. Below means the link layer. So when the link layer receives the packet, it will send the packet there, and as it receives the packet is then ideally it is given to it in a perfect condition, and then it will wait for another packet. So it is finite state machine basically gives us the status of the receiver. So receiver will stay in the waiting state again, right? Now RDT 2.1, here we lift the assumption that the underlying channel is very perfect and every packet is transferred correctly. So here we are introducing the concept of acknowledgements and negative acknowledgements. In our daily conversations as well, if we cannot hear something, then we just acknowledge that I cannot hear this, or if I can hear it correctly, I give a gentle nod, which is a positive acknowledgement. Similarly, in communication, we have acknowledgements and negative acknowledgements, right? And whenever the receiver sends a positive acknowledgement, the sender can get to know that everything is perfect, and whenever a negative acknowledgement is received, then there is some issue and the sender retransmits it, right? So the finite state machine diagram for the same is given here, right? Here basically we have the sender has two states. First it will wait from the call from above to get a packet, and it will wait for acknowledgement or negative acknowledgement, whatever the case is, from the receiver. And the receiver only has one state, to wait, and as it is shown here, if it is corrupt, the received packet is corrupt, then it will perform the action to send the negative acknowledgement. And in this case, when it is not corrupt, it will send the positive acknowledgement or acknowledgement and deliver the data, right? And in the sender side, as we can see, if the negative acknowledgement is received, it will send it again and same in the state, stay in this same state, that is waiting for the acknowledgement or negative acknowledgement. Again, the receiver will send it. Okay, and in the case that positive acknowledgement or acknowledgement is received, we'll go and wait for another packet, right? Here, I guess you guys might have thought about a flaw in the protocol, that until and unless acknowledgement or negative acknowledgement is received, the sender is actually waiting for the acknowledgement. So that is why we have RDT 2.1, where we have a concept of sequence number. So basically here we are introducing sequence numbers to packets, right? And there is 0 and 1 in this case, and whenever a sender sends the packet, it is named either 0 or 1. And when in the same case, when the receiver receives the packet, it acknowledges it along with the package number, right? Which makes it very clear that which packet is lost or which packet needs to be retransmitted. Okay, now this is the receiver side finite state machine diagram. Here again, negative acknowledgement, then we'll be waiting for call from above, so call from below, and negative acknowledgement, it is the same, just for this is one for the packet 0, this is one for the packet 1. It has the similar concept of RDT 2.0. Now comes RDT 2.2. It is NAK free protocol. Here basically it means that the negative acknowledgement is unnecessary, because negative acknowledgement along with the packet number, right, is unnecessary. We can just replace it by packet number and positive acknowledgement. It basically says that if the acknowledgement is received, okay, and the packet number is different, for example in this case our sender is waiting for the acknowledgement of 0th packet, and it receives the acknowledgement of 1 packet, so there is something wrong, so it will have to retransmit it. So in the same case for the receiver, it will wait from 0 and it will resend the packet. It will send the acknowledgement along with the sequence number, and here if the packet is corrupt, it will send the previous sequence number. So basically it knows that we do not have to send this particular sequence number. It will send the other sequence number, which will indicate to the receiver, sorry, the sender, that the acknowledgement is of a different sequence number packet. Thus it doesn't require so it requires a resend, right? Now RDT 3.0, again you might have spotted some flaws in the RDT 2.2, that obviously if the acknowledgement or negative acknowledgement gets lost, then there is no communication at all, right? So for that there is a concept of timer in RDT 3.0. It is introduced, and this is the sender side FSM for the same. So basically here we have a timer and in the sender side, and whenever the acknowledgement is not received until the timeout period, right? So if there's a particular amount of time set, that if it is not received in that time, then the sender will resend it. And at the receiver side, if it has sent the acknowledgement but the acknowledgement was late, then it will simply ignore it, and whenever the acknowledgement reaches to the sender, it will just move the sequence number ahead. So that is the basic concept of RDT 3.0. Now this is the practical example. This is taken from the guys who give the book Top-Down Approach Computer Communication. That's a great slides, and I highly recommend that book as well. RDT 3.0 in action. So here basically the packet 0, as you can see, the packet 0 is sent. It is received perfectly, so it sends the acknowledgement of 0. Packet 1 is sent, acknowledgement is sent, packet 1 acknowledgement. This case is of no loss, ideal case, right? Here it is a case of packet loss. So the receiver never receives the packet, right? And there is a timeout because the receiver has never sent the acknowledgement. So after the timeout, it will resend the packet. Then it receives the acknowledgement. It will go ahead now, right? Then this is the case of acknowledgement loss, right? So what happens is, here the packet is received perfectly, but the acknowledgement is lost, right? So in that case as well, the timeout occurs, and the guy and the sender retransmits the packet, and the receiver detects it is duplicate, so it just sends the acknowledgement, right? And then it goes ahead with packet 0, packet 1, packet 0, packet 1, right? And when there is a case of premature timeout, here as you can see, the sender sends the packet 0, acknowledgement is received, packet 1, it the acknowledgement 1 comes out of time after timeout, right? So after timeout it will resend the packet, obviously. So it detects the duplicate but still sends an acknowledgement, and here the acknowledgement is ignored, right? And here the packet 0 is sent, and here again the packet acknowledgement 0 is received, and everything goes in a straight flow. So that was all about reliable data transfer. Here we have lifted one by one all the protocols, all the assumptions, and thus we have perfected our protocol. But here again there are a lot of things that is used, like we can send multiple packets at the same time. It is done by sequencing and all, but that would be for some other time. This are my references. Computer Networking book, 8th edition. It's a great book, I highly recommend it. And the slides, the animations is taken from the PPT provided by the same author. Thank you.